Lucene searcher in Lucene. Now we are focusing on Lucene searcher. org.apache.lucene.search provides data structures to represent queries, that is term query for individual words, phrase query for phrases, and Boolean query for Boolean combination of queries, and the index searcher which turns queries into top docs. A number of query parsers are provided for producing query structures from strings or XML. Here you can see Lucene searching mechanism. As shown in this figure, the query string requested by the user will be passed by the query parser class in the beginning. Not only just pass the string into the corresponding query object for searching, but also tokenize every word of the indexes using the particular analyzer that is the same as the one during the indexing process. Finally, search the build index. Finally, search the build index files for query results, which will be encapsulated in top docs class and return back to users. Here user is connected to query string. Query string is connected to query parser and analyzer, which has query parser and language analyzer. Query parser is connected to language analyzer. Query parser and analyzer is connected to index files. Index files are connected to return search results. Return search results are connected to documents, and documents are connected to show results to user, and show results to user is connected to user. Here you can see indexing and search. Apache Lucene is an open source Java-based indexing and search technology. It is a technology suitable for any application that requires full text search, especially cross-platform. Lucene works by first indexing the data to be searched, and then using index for searching. Indexing is the process of converting text data into a format that facilitates rapid searching. Lucene stores the data in the form of inverted index. An analogy is an index at the end of a book, and index points to the location of topics that appear in the book. There will be terms created from the input which point to the documents. Terms are indexed, and any search is performed on terms, and related documents are fetched. Lucene index is built over an implementation of the directory class. Lucene supports multiple directory implementation. RAM directory, complete index is kept in the memory. FS directory, complete index is stored in the file system. NIO FS directory supports multiple threads on FS directory. Terms to be created for indexing can be governed by something called analyzers. The analysis, the input to be indexed can be analyzed to extract the terms on which the searching can be done, like extracting word, removing common words and changing the words to lowercase, etc. Analyses are used to both at indexing time and searching time. it is highly recommended to use same analyzers both at index creation and searching time, so that tokens created for searching are created in the same way that the data is indexed. Analyzers internally use tokenizers and filters. Analyzers can take a string as input and returns back to the stream of tokens. Lucene provides some out-of-box analyzers which come handy. In addition to custom analysis can also be created. Some analyzers are simple analyzer, standard analyzer, white space analyzer, n-gram filters, n-gram token filter, h n-gram token filter, length filter. Adding data to an index. Lucene index comprises document which contain fields. Field represent a piece of data queried and retrieved in a search. Field class encapsulate the field name and its value. Lucene provides options to specify if a field needs to be indexed or analyzed, if its value needs to be stored. Field contains terms which are used for querying. Each field has semantics about how it is created and stored, that is tokenized, untokenized, raw data, compressed, etc. Document represent a collection of all fields. Term point to documents. The data that needs to be retrieved through searching needs to be stored in a form of document. Index writer, the class that either creates or maintains an index. Its constructor accepts boolean that can determine whether a new index is created or whether the existing index is open. Document deletion. Lucene provides an index read abstract class that contains methods for deleting documents from an index. Lucene internally refers to document with the document numbers that can change as documents added or deleted from the index. Lucene index optimization. The index optimization is a process to merge all segments to present to an index into a line segment. Optimizing an index is recommended since it improves the search response time. Optimization of index should be done just before closing the index writer. Lucene searching and retrieval. Searching is the process of finding matching document for the input. For the input text. The input text is processed through a chain of analyzers to generate set of terms to be queried. The terms generated from the analysis are used in the query. Lucene search generates a score which is generated using combination of the vector space model VSM of information retrieval and the Boolean model to determine how relevant a given document is to a user's query. Here you can see index in the left side and searching in the right side. Here they are in indexing. It's connected to extract text data, and extract text data is connected to analysis. Analysis. Analysis is connected to the index tokens, and index tokens are connected to Lucene index. Here the extract text data analysis and index tokens are in indexing here. In searching, pass search string and analysis, and create search Lucene query, search index and Lucene index, and retrieve search result, and display results are in searching. And here the pass search string analysis, index tokens, and create Lucene query, search index, Lucene index, and retrieve search index are inside are in Lucene API. Here searching the is connected to a pass search string, and pass search string is connected to analysis. Analysis is connected to create Lucene query. Create Lucene query is connected to search index. Search index is connected to Lucene index. Lucene index is connected to retrieve search result. Retrieve search result is connected to display result and provided the result. Here you can see a basic search application. A lot of application may choose to go for other search integration solutions like Apache Solr, Elasticsearch, which are built on top of Lucene, or just opt in to use NoSQL databases like MongoDB, Cassandra. However, Apache Lucene over its alternative one, the ecosystem, Java ecosystem integration. If your project is built using Java or integrates well with Java, Lucene's integration within the Java ecosystem can be an advantage to granular control. Lucene allows you to control various aspects of indexing and searching, making it suitable for complex use cases. Indexing and searching performance. Lucene, being a low-level solution, is known for its indexing and searching performance, making it a solid choice for projects that require efficient search operations. Ranking control. For ranking control, Lucene provides a high level of control over ranking of search results and what should be shown to other users. If an application faces this requirement, you may opt to go to Apache Lucene as their search solution. In fact, for those of you who want Samsung phone, the search on your device is powered by Lucene. The two main steps involved in search application which Lucene library provides support for are indexing. First one, indexing the document in searchable format. Two, passing the search query and returning the relevant result. Indexing to search large amount of text quickly, you must first index the text and convert it to a format that will let you search in rapidly, eliminating the slow sequential scanning process. This conversion process is called indexing. And its output is called an index. Most such applications use inverted index. The inverted index is designed to facilitate efficient keyword-based searches by storing the mapping of the terms to the document where they apply. The core Lucene classes for indexing. Document. The document class is a Lucene context, refers to the searchable object we want to search for in our search application. Document is a container for various fields. The field class represents the specific attribute or piece of information associated with the document which we want to index and make searchable. It consists of a key value pair, field name, and the content we want to index. Index writer. The index writer class acts as a core component which create and update indexes during the indexing process. Analyzer. The analyzer class is responsible to analyze the document and get the tokens and words from the text which is to be indexed. Directory. The directory class represents the storage location of the indexes on your disk. Searching with Lucene. When you search in Lucene, you formulate queries that target specific field or a combination of of combination of fields. Lucene inverted index efficiently point to the documents that match your query terms, allowing for fast retrieval of relevant documents. The core Lucene classes for searching, the index searcher. The index searcher class acts as a core component which read searches index created after the indexing process. The field class is the lowest unit of searching. It is similar to field indexing process. Query, the query class is an abstract class and contain various utility methods and is the parent of all types of queries that Lucene uses during search process. Term query, the term query class is the most commonly used query object and is the foundation of many complex queries that Lucene can make use of it. Top docs point to the top end search result which matches the search criteria. Query parser, the Lucene query parser utility. Query parser is a utility class that allows you to construct queries using user-friendly query syntax. In Apache Lucene, the analyzer is a critical component used for text processing during both indexing and searching. It's responsible for breaking down text into individual terms, tokens, normalizing those terms, and applying optional transformations like stemming or removing stop words. Here you can see the raw content is connected to acquire content. Acquire content is going to build document. Build document is going to do an analyze document. Analyze document is going to index document. Index document is going to index. And here users are connected to search user interface. Search user interface is connected to build query. Build query is connected to run query. Run query is connected to interacts with index. Run query is connected to render result. Render result is connected to search user interface. Here the search user interface, build query, run query, and index and render result, and acquire content, build document, analyze document, index document, and index document in administration in the level of administration interface and analytic interface. Here you can see a simple searching process. With the searching with Lucene, when you search in Lucene, you formulate queries that target the specific field or combination of fields. Lucene inverted index efficiently point to the document that match your query terms, allowing for fast retrieval of relevant documents. The core Lucene classes for searching is index searcher. The index searcher class acts as a core component which reads and searches index created such indexes created after indexing process. Field field class is the lowest unit of searching. It is similar to field in indexing process. Query, the query class is an abstract class that contains various utility methods and is the parent of all types of queries that Lucene uses during searching process. Term query, the term query class is the most commonly used query object and is the foundation of many complex queries that Lucene can make use of. Top docs point to the top end search results which matches the search criteria. Query parser, the Lucene query parser is the utility that allows you to construct queries using user-friendly syntax. Here the class analyze. The analyzer builds token streams in the package Apache.analysis, that and the analyzer build a token stream which analyze text. It thus represents a policy for extracting index terms from text. Class index searcher implements search over a single index reader. Class index reader an abstract class providing an interface for accessing a point in time view of an index. This is the package Lucene.index. Any changes made in the index via index writer will not be visible until a new index reader is open. It's best to use with directory reader.open index writer to obtain an index reader. If your index writer is in process, when you need to reopen and to see changes in index, it's best to use directory reader.open if change directory reader, since the new reader will share the resources with the previous one when possible. Search of an index is done entirely through this abstract interface, so that the any subclass which implemented is searchable. Class directory in package Lucene.store. A directory provides an abstract layer for storing a list of files. A directory contains only files, no subfolder hierarchy. A class topdocs in org.apache.lucene.search represent hits returned by index searcher .search query int. Here the expression is connected to query parser. Query parser interacts with the analyzer via text fragment, and query parser is connected to index searcher via query object. Index searcher is connected to index row reader, and index reader is connected to directory. And here the indexed search is connected to topdocs. Now we are considering VCM score in the TF IDF similarity defines the component of Lucene scoring. Overriding computation of this component is convenient way to alter Lucene scoring, suggesting here we are discussing how Lucene scoring evolves from underlying information retrieval models to efficient implementation. We are considering on VSM score. Lucene combines Boolean model BM of information retrieval with the vector space model VSM of information retrieval. The documents approved by BM are scored by VSM. In VSM documents and queries, documents and queries are represented in weighted vectors in a multidimensional space where each distinct index term is a dimension. The weights are in TF IDF values. VSM does not require weights to be TF IDF values, but TF IDF values are believed to produce search result of high quality, and so Lucene is used TF IDF. TF and IDF are described in more I'm going to describe in more details now, but for now the compilation, let's just say that given term T and the document or query X, TF function T comma X varies with the number of occurrence of the term T in X. When one increases, so does the other. And the IDF function, the parameter T, Similarity varies with the inverse of the number of index document contained in term T. VCM is score is of document D for query Q is a cosine similarity of the weighted query vectors VQ and VD here, where VQ and VD dot VD is the dot product of weighted vectors, and here the absolute VQ and here the absolute V are the Euclidean norms here, no two norms. Note the above here this equation can be viewed as a dot product of the normalized weighted vectors, in the sense that the dividing VQ by its Euclidean norm is normalizing it to a unit vector. The normalizing normalizing VD to the unit vector is known to be problematic in that it removes all document length information. For some documents, removing this info is probably okay. For example, document made by duplicating certain paragraph 10 times, especially if that paragraph is made of distinct terms. But for the document contain no duplicated paragraph, this might be wrong. To avoid this problem, a different document length normalization factor is used, which normalizes to a vector equal to or larger than the unit vector doc length norm D. At indexing, users here you can see formatting only and the cosine similarity formula here. Now we are considering Lucene conceptual scoring formula. The Lucene refines VSM score for both search quality and usability. Normalizing VD to the unit vector is known to be problematic. That removes all document length information. For some document, removing this info is probably okay. For example, document made by duplicating a certain paragraph 10 times, especially if that paragraph is made of distinct terms. But for the document which contains no duplicated paragraph, this might be wrong. To avoid this problem, different document length normalization factor is used. This which normalizes to a vector equal to or larger than the unit vector doc length norm D. At indexing, users can specify certain document are more important than others by assigning a document boost. For this, the score of each document is also multiplied by its boost value, doc boost D. Lucene is field based, hence each query terms apply to a single field. Document length normalization is by the length of the certain field. In addition to the document boost, there are also document field boost. The same field can be added to a document during the indexing several times, and so the boost of that field is a multiplication of boosts of the separate parts of addition, so part of the field within the document. At search time, users can specify boost to each query, subquery, and each query term. Hence, the contribution of a query term to the score of a document is multiplied by the boost of that query term, query boost Q. The document may match the multi-term query without containing all terms of that query, so this is the correct for some of the queries. Under simplifying assumption of a single field in the index, we get Lucene conceptual scoring formula here. The conceptual formula is a simplification in the sense that one terms and the documents are fielded, and the two boosts are usually per query term rather than per query. Now we describe how Lucene implement this conceptual scoring formula and derive the Lucene's practical scoring function. For efficient score, for efficient score computation, some scoring components are computed and aggregated in advance. Query boost. For the query, actually, for each query term is known when search starts. Query Euclidean norm can be computed when the search starts, and it is independent of the query being scored. From search optimization perspective, it is valid question why bother to normalize the query at all, because all scored documents will be multiplied by the same query Euclidean norm, and hence the documents ranks, their order by score will not be affected by this normalization. There are two good reasons to keep this normalization. Recall the cosine similarity can be used to find how similar two documents are. One can use Lucene for example, clustering and use a document as a query to compute its similarity to other documents. In this use case, it is important that the score document D2, D3 for query D1 is comparable to the score of document D3 for query D2. In other words, the score of document two distinct queries should be comparable. There are other applications that may require this, and this is exactly what normalizing the query vector VQ provides. Comparability to a certain context extent of two or more queries. Document length norm, doc length norm D, and the document boost doc boost D are known at indexing time. They are computed in advance, and their multiplication is saved as a single value in the index. Norm D, index norm D, in the equations of the index norm D. Here you can see a Lucene conceptual scoring formula. Now we are considering Lucene practical scoring function. The document length norm, doc length norm, and the document boost D are known for at indexing time. They are computed in advance, and their multiplication is saved as a single value in the index norm D. Sorry, norm D is not here. In the equations here, the norm T in D means norm field T in doc D, where field T is the field associated with the term T. Lucene's practical scoring function is derived. The color codes demonstrate how it relates to those of the conceptual formula, where TF T in D correlates to terms frequency, defined as a number of times terms T appeared in the currently scored document. Documents that have more occurrences of a given term received a higher score. Note that TF T in Q is assumed to be 1, and therefore it does not appear in this equation. However, if the query contains twice the same term, there will be two term queries with that same term, hence the computation would still be correct, although not very efficient. The default computation for TF T in D in classic similarity is term frequency computation. TF T in D equal frequency to the power half. IDF T stand for inverse document frequency. This value correlates to the inverse of doc freq, the number of documents in which the t time t appears. This means rarer terms gives higher contribution to the total score. IDF t appears in t both in the query and the document. Hence it is squared in the equation. The default computation for IDF t in classic similarity is IDF t equal 1 plus log inverse document frequency computation doc mine plus 1 divided by doc freq plus 1. Sorry, doc 1 plus log as parameters function arguments as doc. Sorry, 1 plus doc open curly brace doc count plus divided by doc freq plus 1 close curly brace. T dot get boost is a search time boost of term t in the query queue as specified in the query text, or as set by wrapping the query boost with boost query. Notice that there is really no direct API for accessing a boost of one term in multi-term query, but rather multi-terms are represented in a query as multi-term query object, and so the boost of a term is query is accessible by calling subquery get boost method. Norm TD is an index time boost factor that slowly depends on the number of tokens of the field in the document, so that shorter field contribute more to the score. So here you can see the Lucene conceptual scoring formula. Here you can see a scorer in a search. Scorer is a core of the search process in Lucene. Scorer is responsible for identifying matches and scoring hits from set of documents present. Scorer is a special class. It is also an extension of a class known as doc id set iterator. Doc id set iterator allows iteration over document IDs, thus allowing seek over the index to get a specific document or to iterate over all documents. Note that the iterator can go forward only. It cannot go backward. This restriction simplifies the underlying codex supporting the iterator. Doc id set iterator provides three useful methods. Doc id method get the internal index document ID for this document. This method always returns monotonically increasing document IDs. Next doc method iterate to the next doc and advance to the location specified. This interface allows the scorer to iterate over all documents and determine whether they are relevant to the query. The scorer works by implementing scorer method on top of iterations. The score method gets the current document ID and gets the current document and returns the score for the same. The index reader has statistic about the current document that can be fully utilized by the scorer to determine the score. If terms vectors are enabled for the field, the scorer can get access the index reader is here. The index reader has statistics about current document that can be fully utilized by the scorer to determine the score. If the term vectors are enabled for the field, and the scorer get access to the term vector and perform even more elaborate operations. How scoring is performed, here you will see how it all fit together. The user issues a query with the instance of a query class. Query is given by given to an index searcher, which first which first rewrite the query recursively, invoking any modification or simplification is possible. Upon completion of the rewrite, the instance of the wait class is created, which is specific to the query plus index searcher combination. This wait will contain all the query specific statistics that apply to the execution of this query. During the scoring, the wait creates a score which iterates over all the documents in the index, filters out the irrelevant document, and applied the scoring algorithm on the candidate documents. The scoring algorithm can be anything that the user chooses to implement or use, but typically is a version of terms, frequency, inverse document, frequency, TF, IDF family. Score interacts with the index reader to get relevant details from the underlying file directory. If a term vector is present, the scorer can choose to use features from that as well as calculate a score for the document. Scorer is expected to return a score per document it iterates on. After scoring completes, the results are returned to a collector, which then chooses the next set of steps. If the top n hits are requested, the collector typically will remain in a priority queue to identify top n hits and then return them back to the user. Here the class query in package org.apache.lucene.search, abstract base class for queries. Class index searcher implements search over a single index reader. Class weight, the expert the calculate query weights and build query scorers. Class scorer, expert common scoring functionality for different types of queries. A scorer exposes an iterator method over documents matching a query in increasing order of the doc ID. Class index reader in package org.apache.lucene.index. Index reader is an abstract class providing an interface for accessing a point-in-time view of an index. Interface collector in org.apache.lucene.search. Expert, the collectors are primarily meant to be used to gather raw results from search and implement scoring or custom filtering, collation, etc. Lucene score collectors are derived from the collector and simple collector. Here the you can see the query. Then query is connected to search index searcher. Index search is connected to wait. Wait is connected to score. Score interacts with index reader, and score is connected to collector. As an example, we can consider org.apache.lucene.search package code to search indices. As an example too, we can consider this code segment. Here the index searcher, class index searcher, implements search over a single index reader. And here you can see the method public top docs search query int n finds the top n hits find the top n hits for query, and this index search is in package org.apache.lucene.search. Here the field score docs the top hits for the query. Here the score docs here the class store docs holds one hit in top docs. Here the query the abstract base class for queries. In this code you can see this now search the index here. And here pass a simple query that searches for text. We can consider this code segment for example 3, and here you can see the class query, the abstract class base class for queries, and this class is in package org.apache.lucene.search. Here you can see term query, a query, the class term query here, a query that matches documents containing a term. This may be combined with other terms with a Boolean query. Here with this constructor, this constructs a query for the term here. Here you can see trace query. A query that matches documents containing a particular sequence of terms here. A trace query is built by a query parser for input like New York. Here is this constructor an empty trace query, and the here with the add set term to end of the query trace, and this example is valid for Lucene 4.7.0. If you are using, for example, Lucene 9, you have to replace this code segment with trace query.builder. Here you can see a Boolean query, a query that matches the document matching Boolean combination of other queries. Here this constructor construct an empty Boolean query with here the adds a clause to a Boolean query. Here the enum boolean clause dot occur. Here occur must use this operator to close for clauses that must appear in the matching document, and in here should use this operator for clauses that should appear in the matching documents, and must not use this operator for clauses that must not appear in the matching documents. This again, this code is valid for Lucene 4.7.0. If you are using Lucene, for example, 9, replace this code segment with boolean query.builder. Here in this code we can consider integrating field values into the score. This query matches the same document as original query, and computes the scores as similarity plus 0.7 multiplied by feature score. Here the boolean query, a query that matches documents matching boolean combinations of other queries. For example, term queries, price queries, or other boolean queries. Here the class builder, boolean query.builder, a builder for boolean queries. The constructor is a solve constructor. Here with the add method, add a new clause to this boolean query.builder. Here you can see the enum boolean clause.occur. Here the enum constant should use this operator for clauses that should appear in the matching documents. Here in the term query, a query that matches the documents containing the term. This may be combined with other terms with a boolean query. The construct boolean query construct term query term. Here construct a query for the term here. Here the method build creates a new boolean query based on the parameters that have been set in the this builder. Here you can see a feature field. This is a field that can be used to store static scoring factors into documents here. Here the new saturation query, this returns a new query that will score document as weight as one float. And a reasonably good default pivot value is computed based on index statistics and is approximately equal to the geometric mean of all values that exist in the index here. This is field name and this is feature name. These are belongs to these are in a different package. Actually, it's in Lucene document. Here you can see the class boost query. A query wrapper that allows to give a boost to the wrapped query. Boost values that are less than 1 will give less importance to this query compared to other ones, while values that are greater than 1 will give a more importance to the scores returned by this query. Here you can see the constructor wrap query in such a way that the produced scores will be boosted by here the boost. This is the query and this is the boost. And here you can see the query builder, boolean query dot builder. Here is add and the build is there. While similarities help score a document relatively to a query, it is also common for documents to hold features that measure the quality of a match. Such features are best integrated into the score by indexing a feature field with the document at index time, and then combining the similarity score and the feature score using a linear combination. Here the query matches the same document as original query and computes scores as similarity score plus 0.7 multiplied by feature score. In this example, you can see integrating field values into a score. In this example, shows how to compute scores as similarity score multiplied by math.log popularity using expressions module. And assuming that values for the popularity field have been set in numeric in a numeric doc values field at the index time. Here the sort field stores information about how to sort documents by terms in an individual field. Fields must be indexed in order to sort by them. Here in the constructor creates a sort by terms in a given field with the type of return type of term values explicitly given. Here short field dot type dot score, and here you can see int, and here you can see compile an expression. Here you can see symbol bindings just maps variables to short field instances. Here create a query that matches based on the original query but scores using expression. Um, the less efficient yet more flexible way of modifying scores is to index scoring features uh, into doc value fields and then combine them with the similarity score using function score query. From the queries module. For instance, this example shows how to compute scores as similarity score multiplied by math.log popularity using expressions module and assuming that values for the popularity field have been set to a numeric doc values field at the index time. As an now we are considering search basics in package octopus.lucene.search. To perform a search, application usually called index.search query int. The public top docs search query int n find the top n hits for a query. This is in the class index searcher, implements search over a single index reader, and in the package octopus.lucene.search. Lucene offers a wide variety of query implementations, most of which are in this in the package of apache.lucene.search or the queries module. These implementations can be combined in a wide variety of ways to provide complex querying capabilities along with the information about where the matches took place in the document collection. The query class section highlights some of the more important query classes. To perform a search, applications usually call index.reader.search query int. Once query has been created and submitted to an index searcher, the scoring process begins. After some infrastructure setup, the control finally passes to the weight implementation and its scorer or bulk scorer instances. Now we are considering term query in query classes. Constructing a term query is as simple as this, and the class term query in package octopus.lucene.search a query that matches document containing a term. This may be combined with other terms with the Boolean query. Of the various implementation of query, the term query is the easiest to understand and the most often used in applications. The term query matches all the documents that contain specific term, which is a word that occurs in a certain field. Thus, the term query identifies and scores all documents that have the field with the specified string in it. Constructing a term query is as simple as this. In this example, the query identifies all documents that have the field named field name and containing the word term. There are the query classes: Boolean query, pointer query, fuzzy query. Now we are considering scoring. The introduction in scoring. Lucene scoring supports a number of pluggable information retrieval models, including these. Lucene scoring is a heart of why we all love Lucene. It's blazingly fast and it hides almost all of the complexity from the user. In a nutshell, it works. At least that is until it doesn't work or doesn't work as one would expect it to work. Then we are left digging into Lucene internals and asking for help in java-user at lucene.apache.org to figure out why the document of five of our query terms score are lower than the different document with only one of the query terms. While this document won't answer your specific scoring issues, it will hopefully point you to the places that can help you figure out what and why Lucene is scoring. You can contact the for the help java-user at lucene.apache.org. Lucene scoring supports a number of pluggable information retrieval models, including vector space model, VSM, probabilistic models such as Okapi, BM25 and DFR, language models. These models can be plugged in via Similarity API and offer extension hooks and parameters for running. In general, Lucene first finds the document that need to be scored based on the Boolean logic in the query specification, and then rank this subset of matching documents via retrieval model. For some valuable references on VSM and IR, in general refer to the Lucene wiki IR references. Now we are considering scoring basics. To be sure to use the useful index searcher.explain query doc to understand how the score for a certain matching document was computed. The method public explanation explain query int doc returns an explanation that describes how doc scored against query in class index is in the class index reader in the package org.apache.lucene.search. The scoring is very much dependent on the way documents are indexed. So it is important to understand indexing. Be sure to use the useful index searcher.explain query.doc to understand how the score for a certain matching document was computed. Generally, the query determines which documents match a binary decision, while similarity determines how to assign scores matching documents. Now we are considering integrating field values into a score in changing scoring in similarity. For instance, this query matches the same document as original query and computes the score matches the same this query matches the same document as original query, and computes scores as similarity score plus 0.7 multiplied by feature score. While the class query in package.apache.lucene.search, the abstract class for queries here. While similarities helped score a document relatively to a query, it also command for a document hold features that measure the quality of a match. Such features are best integrated into the score by indexing feature field with the document at index time, and then combine the similarity score and the feature score using linear combination. For instance, this query matches the same document as original query. And compute the score similarity score plus 0.7 multiplied by feature score. The less efficient yet more flexible way of modifying scorers is to index scoring features into doc value fields and then combine them with the similarity score and then combine them with the similarity score using function score query. From the queries module. For instance, this example shows how to compute score as similarity score multiplied by with the similarity scoring using the function score query from the module queries module. For instance, this example shows how to compute scores as similarity score multiplied by math.log popularity using expressions module. And assuming that values for the popularity field have been set in numeric doc values field at index time. Compile an expression. Simple bindings just maps variables to score field variables to short field instances. Create a query that matches based on the original query but scores using EXPR. Now we are considering custom queries expert level. The query class in custom queries expert level. The query class has several methods that are important for derived classes. The class query in package Lucene.search, the abstract class for queries. In some sense, the query class is where all it begins. Without a query, there would be nothing to score. Furthermore, the query class is the catalyst for other scoring classes, as it is often responsible for creating them or coordinating the functionality between them. The query class has several methods that are important for derived classes. One, create wait, index searcher, score mode, float boost. A wait is the internal representation of the query, so each query implementation must provide an implementation of wait. The rewrite index searcher method, the rewrite queries into primitive queries. Primitive queries are term query, boolean query, and other queries that implement create wait, index searcher, score mode, float boost. Now we are considering search algorithm. In search algorithm, these important objects are involved in the search. The class index searcher in package Lucene.search implements search over a single index reader. This section is mostly notes. Now we are mostly notes on the stepping through a scoring process and served as fertilizer for the earlier sections. In the typical search application, queries pass to an index reader beginning the scoring process. One side of this, inside the index searcher is a collector is used for scoring and sorting of the search results. The important object involved in a search. One, the wait object of the query. The wait object is internal representation of the query that allows the query to be reused by index searcher to the index searcher that initiated the call. 3, the sort object for specifying how to sort the result if the standard score based sort method is not desired. Assuming we are not sorting, since sorting doesn't affect the raw Lucene score, we call one of the search method of the index searcher passing in the wait object created by index searcher.create wait query score mod float and the number of results we want. This method returns top docs object which is an internal collection of the search results. Index searcher creates the top score doc collector and passes it along with the weight to another expert search method. For more on the collector mechanism, see index searcher. The top scorer doc collector uses priority queue to collect the top result for the search. At least we are actually going to score some documents. The score method takes in the collector, most likely the top score doc collector or top field collector, and does it business. Of course, here is where things get involved. Scorer that is returned by the wait object depends on what type of query has submitted. In the most real-world application with multiple query terms, the scorer is going to be Boolean scorer to created from the boolean weight. Assuming boolean score 2, we get an internal scorer based on the required optional prohibited part of the query. Using this internal score, the boolean scorer 2, then proceed into the while loop based on docIterator.nextDoc method. The nextDoc method advances to the next document matching the query. This is an abstract method in the scorer class and is thus overridden by all derived implementation. If you have a simple or simple O query, your internal scorer is most likely a disjunction sum scorer, which essentially combines the scorers from the sub scorers of the odd terms. Now we are considering class expression. The example that shows based on an expression. The Lucene 9.7.0 expression API. The expression module is the new to Lucene 4.6. It provides an API for dynamically computing per document values based on the string expressions. The class expression in package ogla.lucene.expressions, base class that computes the value of an expression for a document. Example that short based on an expression. Here the example that modify the scores produced by the query. Here the compile an expression. Here the simple bindings just maps variables to short field instances. Here the create short field and sort by it reverse order. Here the compile an expression. Simple binding just maps variables to the short field instances. Create a query that matches based on the body colon contents, but scores using exp expression here. Here we are considering Lucene 9.7.0 Facet API, provides Facet indexing and search capabilities. Now we are considering Lucene, the package, the package org.apache.lucene.search.grouping in Lucene 9.7.0 grouping API. A typical use for a generic two-pass search grouping search look like this using the grouping convenience utility, optionally using caching for second pass search. The class group search in package org.apache.lucene.search.grouping convenience class to perform grouping in a non-distributed environment. A typical usage for a generic two-pass grouping search look like this using grouping convenience utility, optionally using caching for second pass search. With regarding package org.apache.lucene.search grouping, this module enables search result grouping with Lucene, where it's the same value in the specified single value group field are grouped together. For example, if you group by an author field, then all documents with the same value of the author fall into the single group. Grouping requires a number of inputs. Group selector, this define how groups are created from values per document. Grouping module ships with selectors for grouping by term or by long or double ranges. Group sort, how the groups are sorted. For you grouping sorting process, each group is represented by the highest sorted document according to the group sort within it. For example, if it's price ascending, then the first group is the one of the lowest price booked within it. Or if you specify relevant group short, then the first group is the one containing highest scoring book. Top n groups, how many top groups to keep. For example, 10 means the top 10 groups are compiled. Group offset, which slice of top groups you want to retrieve. For example, 10 means the top 10 groups are computed. Group offset, which slice of the groups you want to retrieve. For example, 3 means you will get 7 groups back, assuming top n groups is 10. This is useful for paging, where you might show 5 groups per page. Within group sort, how the documents within each groups are sorted. This can be different from the group sort. Max docs per group. How many top documents within each group to keep. Within group offset, which slice of top documents you want to retrieve from each group. The implementation is two pass. First pass grouping collector gathers top groups, and the second pass grouping collector gathers document within these groups. If the search is costly to run, may you want to use caching collector class. Which caches it hits and can quickly replay them for second pass. This way you only run the query once, but you pay a RAM cost to briefly hold all hits. Results are written as top groups. This is within group sort. Groups are defined by group selector implementation. Term group selector groups based on the value of the shorted doc fields. Value source group selector groups based on the value of value source. Double range group selector groups based on the value of a double value source. Long range group selector groups based on the value of a long value source. The known limitation: sorting is not directly supported, though it is not too difficult if you can merge top groups and the top documents per group yourself. Typical usage for generic two-pass grouping search look like using grouping convenience utility, optionally caching for the second pass search. To use the single pass block grouping collector, first at indexing time you must ensure all the docs in the groups are added as a block. And you have some way to find last document of each group. One simple way to do is to add marker binary field. Then and then at the search time here, or alternative use group search convenience utility. Another collector is all groups head collector that can be used to retrieve all most relevant documents per group. Set cache in MB. Require total group count. Render grouped result. Create documents from your source. You can also use the writer.update document. Just be sure you replace then an entire previous doc block with this new one. For example, each group could have a group ID field with the same value for all docs in this group. Render group result. Now we are considering Lucene 9.7.0 highlight API. The package org.apache.lucene.search.highlight here, highlight in the API. This is an example usage. The class highlighter in package org.apache.lucene.search.highlight marks and highlighted terms found in the best sections of text using configurable fragmenter, scorer, formatter, encoder, tokenizers. The highlight package contains classes to provide keyword in context features typically used in highlight search terms in the text result pages. The highlighter class is a central component that can be used to extract most interesting sections of a piece of text and highlighting them with the help of fragmentator, fragment score, and formatter classes. Here is an example usage. Above create the documents with two fields, one with the term vectors TV and one without no TV. Term vector. Now we are considering package org.apache.lucene.monitor in Lucene 9.7.0 monitor API. A number of method types are included. The class monitor in package org.apache.lucene.monitor. A monitor contains a set of query objects with associated IDs, and efficiently matches them against set of document objects. A number of matches types included here. The and the in the package Lucene.monitor, the monitoring framework, this package contains classes to allow monitoring of a stream of document with a set of queries. Here a number of matcher types are included. Query match.simple matcher just returns the set of query IDs that a document has matched. Scoring match with similarity Lucene.search.similarities returns a set of matching queries with the scores that each one records against document. Similar to scoring match but include full explanation, returns the matching queries along with the matching terms of each query. Matches can be wrapped in partition matcher or parallel matcher to increase performance in low currency systems. Now we are considering Lucene the Lucene 9.7.0 Spatial Extras API, the Spatial Extras module for Apache Lucene. The Spatial Extras module uses Spatial 4J heavily. Spatial 4J is an ASL license library with these capabilities here. The class Spatial strategy in package Lucene.spatial. The Spatial strategy encapsulates an approach to indexing and searching based on shapes. The Spatial Extras module new to Lucene for 6.5 is new home for our original Lucene Spatial module. The principal interface is this module is Spatial strategy, which can calculate approach to indexing and searching based on shapes. Different strategies have different features and performance profiles, which are documented at each strategy's implementation class level. For some sample code, the Spatial Extras module uses Spatial 4J heavily. The Spatial 4J is an ASL license library with these capabilities. Provides shape implementation, namely point, rectangle, and circle. Both geospatial context and plain 2D Euclidean Cartesian contexts are supported. With additional dependency, it adds polygon and other geometry shape supports via integration with JTS topology suite. This include dateline wrap support, shape parsing and serialization, including well-known text WKT via JTS, distance and other spatial related math calculations. Historical note, the Spatial Extras module was once known as Lucene Spatial Playground LSP as an external project. In March 2012, the LSP split into Spatial module as part of the Lucene and Spatial 4J externally. A large chunk of LSP implementation originated as SO LR2155, which uses tri-prefix tree algorithms with geohash encoding. That approach is implemented in recursive prefix tree strategy today. An example, we can consider class index searcher dot too many clauses thrown when an attempt is made to add more than get max clause count clauses. This typically happens if a prefix query, fuzzy query, wildcard query, or term range query is expanded to many terms during search. This is in package org.apache.lucene.search. As an error example, we can consider this error o.e.b. Elasticsearch uncaught exception handler. Fatal error occurred in thread existing and etc. And here at org.apache.lucene.search search.searcher.search index searcher.java 665 etc. This is occurred in the environment with Elastic Stack and Elasticsearch.